Right, so then let me introduce the next speaker. The next speaker is Massimo Mannarelli. He will talk about meson condensation and chiral perturbation theory. So could you please share your screen and then start?
Can you see it now?
Yes.
Okay.
Well, it's not. Yeah, now it's in full screen.
Right. Okay. Okay. Thanks for the invitation and to show my my work. It's on meson condensation and mainly on using chiral perturbation theory. The thing is, so the outline is this one. I will give a short introduction of motivation, and then I will discuss symmetries and symmetry breaking and why they're relevant for the discussion of meson condensation. And then we introduce some methods and compare them. And then I will discuss two topics that I've been developing recently, multi-meson condensation and on crystalline or solitonic-like phase. So hadronic phases. So it's describing hadronic matter. We know it's difficult, basically because we would like to reduce everything into elementary objects, and this is efficiently done actually when you use deep analysis scattering, or so we know what are the constituents of matter. The thing is that, however, there are two main problems. One is confinement, and the other thing is that even if you have the confined matter, it's still strongly interacting in labs, I mean, Frick, LHC, or even inside compact stellar objects. But anyway, I mean, since we know that QCD is asymptotically free, we know that at a center point, the quark matter should be liberated, using the words of Cabibbo and Parisi. And at a certain point, you should form a quark plasma, the IT, and presumably at increasing baronic density, some kind of color superconducting phase. When you increase the isospin chemical potential, it should form the pion condensate, and if all these quantities are small, then you are in the standard hadronic phase. The point is that the nice thing, I mean, this is certainly a cartoon, okay? These are just done by hand, lines done by hand. We'll come back to the QCD phase diagram at a certain point. The nice thing is that actually you can specify the various phases by their condensates. So there's a chiral condensate for the hadronic gas, corresponding to the dipole condensate, and a meson superfluid is or pion condensate is a psi bar sigma 2 psi, or more involved if you have cation condensation, and the quark plasma is not condensate, so it's the state, if you wish, of a maximum disorder somehow. And this condensate breaks or locks the symmetries of QCD in a different way, and depending on how it's broken, then you have a phase with different properties. How to make progress? In my opinion, any route and physically sound method should be employed, and this is done, as example, if you change the pion mass, or if you use extraordinarily large magnetic field, and somehow you go beyond the physical sheet, I mean, what is realized in nature. And this is really helpful. The other point is which methods you can use. Certainly in Nambu-Yonah Lasinio-like method, or chiral perturbation theories and rules, and whatever you think is appropriate for describing matter. And it is helpful to make progress. One important distinction, which however one has to do, is that the properties of matter in heavy ion collision and in compact stars are, first of all, there's of course the fact that heavy ion collision produce hot matter at the vanishing baryonic chemical potential, and while compact stars are dense matter which is catalyzed, which means in net electroweak equilibrium, so it is statistically stable. Okay. So if we plug heavy ion collision and compact stars in the QCD phase diagram, we have this kind of So there's some kind of isospin asymmetry in compact stars because we have more neutrons and protons as a sample. Also, we have electrons to make things neutral, and also we can have even strangeness if we have if we're populating hyperons as an example. There is a famous hyperon puzzle for compact stars. Anyway, these are the possible phases. How can we explore them? Well, certainly Lattice QCD is very helpful, but as you can see from the picture, it stays at low baronic chemical potential and isospin chemical potential, certainly exceeding the pion mass, maybe 2 times pion mass, as was the chair saying before. That it really depends on the lattice side, but of course that also means that I mean, how trustable are your error bars and so on and so forth. Then you can use perturbative methods like perturbative QCD. Here I've been very generous with perturbative QCD. I mean also resummation, and then you have chiral perturbation theory and the NGL-like model. Now the good thing about all of these things is that they have, you can see, a certain overlap among them, especially close to the t equals 0 and mu I, sorry, to the t-axis and mu I axis. There is a much less overlap as you increase the mu b, especially because lattice simulation are not dual because of the very well-known sign problem when you have a mu b different from 0. So what can we learn from symmetries? Well, first of all, we know that we can classify quarks and also mesons using hypercharge and isospin. So this is on the I don't know whether you can see my pointer, probably no. We can classify kaons, pions, and the eta. This is so the octet and the singlet. And they have very precise values of strangeness or hypercharge and isospin. Just using this information, we know that pions have an isospin charge, so their energy should be shifted with the Zeeman or better Stark-like effect by a quantity proportional to mu I. So it's an energy shift. No, something should happen when their effective mass becomes 0. What happens, what we typically expect is that the stable vacuum becomes, the naive vacuum becomes unstable, and that there is so the symmetry breaking to a phase which is a reduced symmetry. I mean, there's only symmetry in for rotation around this vacuum. And this is the global symmetry breaking, which is then followed by the appearance of an Ambu-Goldstone boson. And certainly this object, which becomes massless, is the putative Ambu-Goldstone boson that appears. And we can do this thing as well, introducing kaons. The mass splitting of the meson, the meson and the kaon masses is reported in this figure here. And so as we increase the isospin and strangeness of our system, we have a splitting of the masses of kaons and pions. So any degeneracy is removed by isospin and strangeness. And this is simply from this plot, you can actually determine the diagram that Jens was showing before. At least the hexagon, the red hexagon, which is in the center, which corresponds to the second order phase transition, is just obtained using the expression I've written before for the masses. While the dashed line corresponds to first order phase transition, and actually you cannot derive these lines from that figure, but certainly there's a first of all symmetry that you can use to draw this picture. And the other thing is that since there's a competition of condensates, you certainly expect a first order phase transition between say the phases with the pion and kaon condensation. So I think it should be now clear that this is some really robust results, which, I mean, you do not really need a chiral perturbation theory or any other theory to make to draw this picture, but to make progress you need it. the thing is that what the state of matter we want to describe is a Bose-Einstein condensate. And basically, the thing is that when you reduce the temperature in a bosonic system, I mean, you can have a large occupation number of the lowest lying level. And in order to have this, the recipe is that you need bosons, or boson-like objects like Cooper pairs. The system should be cold because there's a fight between thermal disorder and quantum coherence, and the particle must be stable. So for pions, I mean, we know that pions are bosons. We can cool them. I mean, they are really cool inside compass stars, but they are not stable. They tend to weak decay and typically muons because of velocity. Anyway, they decay in leptons. The thing is that we can, however, probably block this if we change the energy levels of electrons. I mean, somehow you can pump up the number of electrons so the Fermi sphere goes up, or you can think that you're lowering actually the effective mass of the pion. So at this point, there is actually a statistically stable matter in the sense that the number of pions is statistically conserved. What are the possible matters? So there's certainly a Lattice QCD. The next talk, I think, will be discussing this, and basically very successful because it reproduces the two basic properties of QCD, which is asymptotic freedom and confinement. However, it can be done at mu I different from 0. For small, actually, mu s, strangeness chemical potential, but certainly 0 mu b. The other method is NJ-like modeling, in which you replace the QCD interaction mediated by gluons by local interactions, a contact interaction like in Fermi theory. And it is very nice because chiral symmetry is realized and spontaneously broken as in QCD. However, the shortcoming is that actually one needs to fix the coupling, the regularization scheme, and the mass system of these fermions. There's no gauge dynamics, so there is no confinement, and there is no expansion parameter, so it's hard to improve and keep control on the results. Chiral perturbation theory, on the other hand, it's a realization of hadronic matter at low energy, so it's for energy below the chiral breaking scale, which is of the order 1 GeV. The qualitative recipe is basically that it's one variation derived at the non-perturbative vacuum and then expanded on that vacuum for a small momenta. Since you're expanding, you have control parameters. That's a very good news. And typically, we do not want to include vector mesons and baryons, and that's the reason why we stay below the proton mass and the rho mass. In vacuum, it's KPT is very successful at just presenting one results. To point one important aspect is that in order to make predictions to be predictive, this theory needs to fix so-called low energy constants, which, for example, in the T-channel cross section are simply the pion mass and the F pi. But once you fix this, you can predict the amplitude for any other processes. I mean, any other process like pi, 4 pi, 6 pi, 8 pi, or whatever you have in mind. The theory is predictive. And it can be systematically improved. What are the shortcomings? That you need to fix the low energy constants, and certainly, I mean, as has been shown in the previous talk, they are running. Need to know the correct degrees of freedom, and you have not access to the macroscopic description. I mean, there's no quark level in the KPT description. Lagrangian, which has also been shown from the previous talk, is at order p square, is simply this expression here, where if you want to describe the SU2 sector, we simply have to use this parameterization of sigma, of this unimodular field. The low energy constants here are simply F pi and the masses, which is in this object here. And I choose this decomposition of the sigma in, say, in 3 different fields, alpha, theta, and phi, and which correspond to the 3 degrees of freedom. You can think of them as the pions. But since in the broken phase, pions are mixed, classification using pi plus, pi minus, and pi naught is not really much helpful in the broken phase. The very good thing about this of chiral perturbation theory is that at least at tree level, it's very easy, and it is quite easy to get results. If you just plug the static and homogeneous web, I mean, now it's called sigma bar, in the Lagrangian, you get this expression here, and you get that by simply maximizing Lagrangian, you have the first order phase transition. I mean, for mu I equal m pi, there is a change of symmetry from the normal phase to the broken phase, where you have a residual O2 symmetry, which is exactly the direction spanned by the Navier-Stokes boson. So simply, I mean, this expression is just can be computed very, very quickly. So it gives us exactly what we were expecting to get. How can we make progress? Is in this simple way, comparing Lattice QCD with the Nambu-Iono-Lasinio and chiral perturbation theory. I've been working for ages on color superconductors, and I've always dreamt to have a figure like this for the quark, for the diquark condensate. Instead, this is of course obtained comparing Lattice QCD results for pion condensate, which are these square ears. This is not really up to date, but it has all the necessary information. The solid blue line is Nambu-Iono-Lasinio model, and the dashed line is chiral perturbation theory. As you can see, I mean, close to mu I equal m pi, all of them predicted the same behavior of the phase transition, which is really a very nice and important result. This is just telling you that the result is extremely, extremely robust. And it is only leading order chiral perturbation theory. If you improve chiral perturbation theory, as Jens has been showing before, you even get a better agreement. Okay, sigma is instead the standard chiral condensate. Then you can, if you put non-zero non-vanishing temperature as a system at finite temperature, you can still compare the result. But as you can see, the agreement between the NJR, which is still the blue line here, the pion condensate and Lattice QCD results is less good. There's a lot of work that has to be done in this direction to improve the agreement between these three methods. But another interesting result is instead this one. If we plot the energy over the Stefan Boltzmann energy as a mu I. As you can see, this lattice data have a peak for mu I close to m pi. It's also shown the perturbative results, which correspond to the orange line. Instead, the chiral perturbation theory is the dashed black line. Well, as you can see, there's a very good agreement between chiral perturbation theory and Lattice QCD. But the astonishing thing somehow is that the position of the peak obtained in Lattice QCD with the increasing lattice spin, I mean, in the continuum limit somehow, is 1.275 m pi. And instead, a leading order chiral perturbation theory gives simply an analytic expression, which is extremely close to. This is just to convince you that chiral perturbation theory works extremely well, close to at least for mu I of the order of m pi. Then the agreement is somehow lost for larger values of m pi, but also Lattice QCD has a problem. So this is somehow an updated picture of the QCD phase diagram, where it's shown the phase transition between the hadronic gas and the pion condensate phase. There are still many question marks, but at least this part of the QCD phase diagram has been attacked, I would say, successfully described. Now, since I've been asked to be proposed and to present somehow results that maybe are a bit puzzling, I decided to present two of my works. One is on multi-meson condensation, and this has been done with Luca Lepori, which is a postdoc in Pisa. And the idea basically is that to have the simultaneous condensation of two species of mesons. So the basic idea was to simultaneously describe pion and kaon condensation, as much as one can describe, say, helium-3, helium-4 superfluids in condensate matter or superfluid systems. Or in compact stars, neutrons and protons are simultaneously superfluid, actually. Protons are superconducting. So the thing that we would expect is that there's some control parameter in which you can span between the single superfluid phase, say SF2, to a simultaneous condensation, if it is possible, if it exists, and then the condensation of the other superfluid. And so the idea should be that there is a pion superfluid bubble, since it's a first order phase transition, there can be bubble formation, and the kaon superfluid C, or the opposite, of course, the opposite situation. And or they may coexist, so they can have a simultaneous condensation of the two. So how to describe a multi-meson system? We certainly have to have a symmetry group which is simply G1 times G2, where these are two identical copies of SU and F times SU and F. And in principle, I can, if they are not interacting, I can arbitrarily rotate the two fields that describes the meson in one group and mesons in the other. So the most general leading order Lagrangian that I can write from an interacting systems is this one. Now, what about the possible interaction terms? So we analyze basically two kinds of interaction. One is, say, unlocking interaction, in which basically the global group is unbroken, and at least at the Lagrangian level. And this is, however, a order P4 in chiral perturbation theory, so it's somehow subleading. Instead, there is a weird interaction, which is this one, which actually locks G1 and G2 to a diagonal group. And it is actually order P square. So if you think about now the system, basically it's made of two identical, but maybe you can take F pi 1 different from F pi 2. So these are two ensemble of pions, with simply different by the decay constant. And you can change mu1 or mu2, and you have a phase diagram of this type. Simply, if you change the interaction, you can have in the region called SCO, you can have a simultaneous condensation of the two, and this is a change on the depending on the sign of this intraspecies interaction. So somehow this is expected. This is actually what has been derived also in superfluid system like helium-3, helium-4. Okay, very, very similar to this the thing. So there is exactly we have obtained basically this kind of plot, this kind of transition, simply following, say, the red line. You have a transition from superfluid 2 to simultaneous condensation to superfluid 1. But then if you use the lock interaction, we find something weird, which is the fact that there's only a simultaneous condensation apart from the axis gamma 1 and gamma 2, but apart from there, I mean, you have always simultaneous condensation. If you increase this coupling, the normal phase shrinks. And it seems that you can crank up this number, I mean, extremely large values, so that the normal phase completely disappears. But is this physical or not? And what we actually found is that as you increase K, notice that M1 and 2 are not the real masses. The masses are obtained by diagonalizing the propagator. So this is these are the real masses of the two pions that depend on K. So one of the two modes becomes unstable. So the mass becomes negative. So it's becoming a tachyonic mode. And so the thing is that we then thought, I mean, why?
Massimo, sorry to interrupt. So
yeah.
You have 1 more minute. So could you start to?
Yeah.
So.
Yeah, okay. So the thing is that we analyze this with a toy model, and we believe that this is basically related to phase separation of the, so there should be a bubble-like system like this. Very quickly, sorry I'm late, I want to show this, this result obtained for the solitonic phase. So once again, we start from the same kind of field, but we look for classical equation of motion. So now the three fields are named alpha, theta, and phi. I think that's before. And then we analyzed the possibly inhomogeneous phases, solitonic-like. So we discretize the system if we put in a box, and we pose the Dirichlet boundary conditions, and so we make some assumption on the possible dependence of the fields on the t and theta, r, and phi. So we'll so the phi fields basically obey the free field equation, which is due to the fact that it is an Ambo-Goldstone boson, so it's massless, and it can behave as a free field if one uses this parameterization of alpha, theta, and phi. And one can choose a dynamical field solution or a solitonic-like solution. So the existence of solitonic-like solution, I mean, is very interesting in our opinion. And then one can do the same for theta, and one is a Sine-Gordon-like equation with clearly the typical kink solution. And also in this case, one can take a simplified version with simply a linear dependence on theta. Finally, there is the alpha modulation, which is the third field, also in this case a static, a static solution. And basically, one can easily integrate the corresponding differential equation and obtain this result. Interesting thing is that this system has a topological charge. So this system is protected from decay. And we computed this topological charge, which is an integer number, and depends on the value of Q, which is one of the parameters which determines the solitonic solution. Well, okay, this is just an advertise for my review on the Meson condensation. In case you want to know more, this is also this is an open access, so you can freely download it. And I go to my conclusions, which is basically the following. Since we want to understand the QCD, one possible way is to attack the phase diagram from the direction which presents less resistance than others. And certainly in the direction of mu I with the pion condensation, and is doable. This direction. I mean, this is a path that we can use to get information on QCD. And the thing is that we have several methods, and I've just shown Lattice QCD and JL and perturbation theory, and they simultaneously work. So our results are certainly robust. And the thing is that one possible question for lattice people is whether it's possible to realize inhomogeneous phases to look for solitonic-like solution on the lattice.
Right.
Okay. Thanks. I'm done. Sorry for
being late. Thank you very much. So now also almost the time for questions is up. But if there is a very short one, then feel free to ask it. Also, thank you again for your very nice talk and also for these very interesting questions. I agree with the last one also. Very much. So is there any short question or Ricardo Farias, so please go ahead.
Thanks for a good talk, Massimo. I have a question that is about the coupling constants. Usually yes. we are assuming that the coupling constants in NGL model can fill and decrease with magnet field and with temperature. I would like to see your opinion if can be also physical assume that the NGL coupling constant can fill the isospin chemical potential.
Yeah, I mean, the thing is that the proper way of fixing the coupling constant and the regularization scheme is to fix them to some physical quantity or using lattice QCD. Okay. So if you find a combination of coupling constant and say cutoff or whatever regularization scheme that you are using in NGL to reproduce physical observables, and you find that there is a dependence of the coupling constant on μi, then I think you're allowed to do that. But somehow the problem remains. I mean, NGL has no small parameter. It's not an expansion. Okay, it's an effective model which was introduced by Nambu and Lasinio for describing superconducting matter. So it's, in my opinion, I mean, you can certainly, I mean, improve it. You can put a Topological loop inside in order to have some gauge dynamics. You can have a dependence on isospin or baryonic chemical potential, but the cleanest way to do it is simply to fix the value, say, to reproduce the pion condensate or the chiral condensate and low energy properties of the system, I would say. So I have no answer to your question, because that depends really a lot on whether you can gain something or not, putting a μi dependence on G. In my opinion, it's hard to say this. Okay.
All right. So maybe I cut in here. So thank you for the question and the answer, of course. So maybe we can also discuss this some more in the discussion session, and then maybe we just move on to stay on time. So yeah. Heading over
Thanks
to
a lot.
now. Thank you once more.